Hello guys, welcome back to my channel. Memo African Motives. Still working on the question paper of February 2022 on engineering science N2. Here we are now back to heat. So we have got the question which is on heat that we just want to focus on. So if you're new to my channel, guys, don't freak out. If you're new, don't just make sure that you become part of the family by subscribing, and also don't forget, guys, to share our videos to your friends and colleagues so that they also can benefit from this information that you're having from Memo African Motives. Okay, so let's quickly rush through the question that we are given on heat. So we're given the first part there on heat on 7.1 actually, to explain the term heat lost, the heat that is lost, and we've got 2 marks for that. Okay, so remember that heat, it's Q, which is actually the energy there. So heat lost, it is when there is a decrease. So whenever you're talking about a decrease, it's actually a drop that is occurring there in the final temperature. So there's a decrease in the final temperature as compared to the initial temperature. Okay, so there's a loss or a decrease. Whilst for heat gained, there is going to be an increase. There is going to be an increase or a gain there, or a gain. So to gain, that is to increase from what is given, that is heat gained. So it's going to increase. But if it is heat lost, that is, there is going to be a reduction. There is going to be a decrease. So that is what we are going to have in this. So it's going to be a reduction in the final. Okay, so you are reducing there. So that's what you have. So the key part is lost here. You are losing, you are decreasing, you are reducing. There's a drop. Okay, when there is a gain, when it is gained, it's increasing. All right, that is the concept there. So on 7.2, define the term specific heat capacity. Okay, so the specific heat capacity, we know that it is the quantity of heat required to raise the temperature of 1 kg of the substance by 1 degree Celsius. So the 1 kg is actually for the mass of the given substance here. So we are increasing it by 1 degree Celsius, which is actually, that's why you are given the specific heat capacity as joules per kg degree Celsius. So we are talking about mass and affected by a temperature of 1 degree Celsius. So that's the concept there. So that was the concept there on 7.2. Then on 7.3, a 40 kg welded steel plate is with the temperature of 94 degrees Celsius is dipped in water, in the water container, with the water temperature being 18 degrees Celsius. The final temperature. Okay, so this is supposed to be the final temperature. There is no the final temperature of water, and the steel plate is 60 degrees Celsius. All right. We've talked about this type of equation, if you still remember, guys. So it is best, like I always say, that you list the information. We've got the steel and you have got the water here. These are the 2 requirements that you actually have. So the steel was placed in water, so which means it's going to reduce its temperature, but it had a mass of 40 kgs of steel. So the mass of steel is 40 kgs. So you can write this as ms to represent the mass of steel. All right. Then definitely when there's a steel, we are going to have the specific heat capacity of steel. All right. I'm going to, or let me just show you now the specific heat capacity of steel here, which is 500 joules per this one, 500 joules. So you've got 500 joules per kg degree Celsius. That's per kg degree Celsius, like that. All right. We also have for water. So let's just write this specific heat capacity also for water. The specific heat capacity for water is 4187 joules per. Okay. So we've got 4187 joules per kg degree Celsius. That's what we have there. All right. So what happened is that it with temperature 94 degrees Celsius. So this is the temperature of the steel before anything happens. It was 94 degrees Celsius. All right. Then is dipped in water container with the water temperature being, so this is the temperature of water, so the water at its own temperature at that moment, which was 18 degrees Celsius. All right, so this is the temperature, 18 degrees Celsius, like that. Then the final temperature of water and steel is 60 degrees Celsius, which means the final temperature is the temperature for both after, because now the steel, because remember the steel is being put inside the water like this, so this is the temperature of both the steel and the water, so that's your T2. So it's not affecting only steel, but it's affecting water and steel, which is 60 degrees Celsius. So that's your T2 of the system. So you've got 60 degrees Celsius. All right. So let's just take a consideration before the question. Let's just analyze from the information. Our steel is a temperature of 94. After that, its temperature is now 60 degrees. Water was having a temperature of 18. After that, it is now having a temperature of 60 degrees. So as you can see that water is gained. So it gained here, water gained, because from 18 to 60 there's an increase. Remember what we defined from heat loss and heat gained. Heat loss, you are losing, like what happened to steel. Steel started with 94, at the end it's at 60, so there is a loss. So here we have got heat lost, and here we have got heat gained. So that is what happened there, because there is a loss in temperature, there is a reduction in temperature, so there is heat lost. There is an increase in temperature, so there is heat gained there. Okay, so once you know these properties, it's very easier for you to answer this question, which is calculate the mass of water in the container. So the mass of water in the container, we're going to use the relationship between the heat lost and the heat gained, that they are equal. So this is going to be 7.31. Is it so? 7.31, yes. So we are going to have 7.31, where we are saying that heat lost will be equal to the heat that is being gained. So if this be the relationship, therefore it's now easier for us to have this, because what lost heat is the steel, and what gained is the water. So we've got the steel here, and we've got the water here. So we've got, remember, the heat lost, it's mass times the specific heat capacity times the change in temperature. Let me just write this. All right, times the change. So this is mass of steel, the specific heat capacity of steel. This is the mass of water, the specific heat capacity of water. But this change in temperature is going to be written like this. It's going to be written like, because it this one it lost, so we are going to subtract this one for steel minus the final temperature, which is T2. So it's TS minus T2. Don't confuse on steel here, but most of you confuse here, which is equal to mass of water, specific heat capacity of water, times the change in temperature of water. Since it gained, you are going to subtract final minus initial, so it's 60 minus 18. So where it gained, you subtract final minus initial. Okay, I'm not substituting, guys, sorry. It's supposed to be T2 minus TW, so that we can substitute it once. All right, so now let's substitute. We've got the mass of steel, that's 40. So we've got 40 times the specific heat capacity of steel, which is 500. So we've got 500 there, by the change in temperature, that's temperature of steel 94 minus T2 60. So it's 94 minus 60, that's for steel. So you're done with steel. We move on to water. Mass of water, this is the one that we want to calculate, because we do not have the mass of water here. So we are going to have the mass of water times the specific heat capacity of water, which is this one, specific heat capacity of water, which is 4187, into T2 minus T water. T2, that's 60 minus T water, which is 18. So it's 60 minus 18. All right, so that's the concept there. So what you're going to do, what I'm advising you to do, guys, is to use your calculator at once to simplify this whole value. So you multiply, open bracket like that. So you're going to obtain something like 680,000, which is equal to, you multiply also these. So if you multiply these, you are going to obtain 175,000 actually, 854. This is what you're going to obtain if you multiply these together, okay, times mass of water. So in order for you to find the mass of water, you divide. So you're going to divide both sides by 175,000, 175,854. 175,854. So if you divide both sides, guys, don't freak out. This is going to be mass of water. You use your calculator here. All right, so if you divide properly, you're going to obtain this endless decimal, 3,8666,844. That's 087, something like that. Okay, so the mass of water at the end is going to be, you can round off to 3 decimal places depending, but mostly I use 3 decimal places. That's 1, 2, 3. So it's 3, 8, 6. This 8 is going to change this into 7. This is mass of water, which is in kgs. Okay, so it's going to be 3,867 kgs. All right, so that's it, guys. So yeah, that's what you were supposed to do there in order for you to have the mass of water. So you use the relationship between the heat that is lost and the heat that is that is gained. That is, heat lost is equal to heat that is gained. That is how you can calculate this. All right, so let's see another part on 7.3 to calculate the energy gained by water. So the energy gained by water, that is the heat, which is this one. So remember the formula that we had there. So guys, there's something also that you are supposed to take note. It's because we have the mass of water, which is actually, but these are supposed to be equal. But let's just see what you're going to have on 7.32. So we know that for water, we are going to have mass times the specific heat capacity times the change in temperature. All right, so let's just substitute this into the properties of water. So we've got the mass of water, we have got it. This is the mass of water that we obtained, 3.686. It's 867 by the specific heat capacity of water. It doesn't change. The one that we had, which is 4187. So you've got 4187 by the change in temperature. It does not change. Also, this is the change in temperature, 60 minus 18. So it's 60 minus 18 like this. So it's because of the rounding off that we did here. That is why our answers are not going to be that exact. Okay, so if you multiply this in your calculator, you're going to have something like 680027,418. All right, these are now joules. All right, so you can round off to kilo, which is going to be 123. Just divide by 1000, which is 680.027. Okay, it's going to be 0.027 kilojoules. If you want to round off to joules, okay, you can round off to kilojoules, but you can just leave it in joules like that. That is what you're given. So you can actually leave it like that. So there's nothing that was much important there. You can just leave your answer in that manner, but that is what you're asked to do. All right, then on 7.4, actually you're given a copper rod with a length of 5 meters and a length of and the temperature of 20 degrees Celsius is exposed to heat with a temperature of 400 degrees Celsius. Calculate the change in length of the rod in millimeters. So take note, we are given the original length in meters and the answer is supposed to be in millimeters. Okay, so that's on 7.4. So you know that whenever you are given the original length and so forth, so you can just list down the information that you are given. This is the length of the rod, a copper rod. So you are working with a copper rod. So it's very, very important that you know what you are working with. So you've got the length, the original length of the copper rod, which is 5 meters, the temperature and the final temperature. Okay, so that's the length, original length, which is 5 meters. The initial temperature, initially this rod was at 20 degrees Celsius, then finally at 400. All right, so that's 20 degrees Celsius, then the final temperature, which is 400 degrees Celsius. So what we are going to have from the copper rod, why do they give us this copper rod? We are going to find the linear coefficient of expansion of the copper rod. All right, so the linear coefficient of expansion is given here. The linear coefficient expansion of copper, all right, that is 0 point. So you're going to just have it in a straight manner. This one linear coefficient of expansion of copper, something like this. All right, so you're going to have that value, which is actually 0.00, this value. Okay, so you have got 0 point, which is equal to 0.000 0 again 17. All right, per degree Celsius. All right, so that's the unit. So the unit is per degree Celsius. So how why are we listing this information? We also know that once we have the information, it's very easier for us now to calculate the change in length. We know that we have got a formula here for this change in what? Change in length. So what is the formula, guys? All right, remember that the formula is change in length is equal to original length times the linear coefficient of expansion times the change in temperature, like that. All right, so this is what you're going to have for the change in length. So let's substitute here. So the change in length is going to be the original length, which is 5 meters, times the specific, which is the linear coefficient, which is 0.00. I don't know where I'm getting this specific. All right, multiply by the change in temperature. So the change in temperature, actually it means T2 minus T1. That's the change in temperature, T2 minus T1. Okay, so that's your T2 and that's your T1. So it's going to be 400 minus T1, which is 20, like that. All right, so that is what you're going to have from your calculator, guys. So you have to multiply everything there, which is going to give you 0.0323, which is in meters. All right, but take note, guys, the question is have or express this in millimeters. So your answer should be in millimeters. So millimeters, remember, how do you convert to millimeters? Which means you have to move 3 commas, or you just multiply by 1,000. Okay, because milli, to remove milli, you multiply by 10 to the power minus 3. That is to remove. When you are removing, you multiply by 10 to the power minus 3, which means to put back, you multiply by 10 to the power 3. So that is what you're going to do, to put back millimeters. To remove millimeters, you multiply. To put back millimeters, you multiply by the opposite. So it's going to be a positive. So you're going to multiply by 10 to the power 3, which is 1,000. So the moment you multiply by 10 to the power 3, you're going to obtain 32,3, which is now in millimeters. So that is your change in length in millimeters now. So take note, guys, that's the relationship. To remove millimeters, you multiply by 10 to the power minus 3. All right. To put back these millimeters, you multiply by 1,000, which is actually the opposite of what you did. You multiplied by 10 to the power minus 3. This time you multiply by 10 to the power minus 3, or you divide by 10 to the power minus 3. That's the easiest way, actually. Yeah, that's the easiest way you can obtain the same thing. So what I'm simply saying is that the opposite, you can actually divide, because you multiplied to obtain that. So you can actually divide like this. It's only that this is too much, there's too much light, but see what I'm saying. 0.2323 divide by 10 to the exponent. If you divide, you use -3 as it was. So still you're going to obtain the same answer of 32,3. So it's a matter of the way that you want to have this. Okay, so that's it, guys, on this question. As you can see, we've got 10 marks for that working on heat. That was 10 marks from this question paper, everything there. So guys, that's it from Memo African Motives, working on question papers and revisions for engineering science N2. So if you are actually new, guys, don't freak out, be part of the family. Share our videos also to your friends and colleagues outside there, so that they also can have a benefit from this information. So please, guys, we beg you to share these videos to your friends. Okay, so that's it, guys, on HIT from February 22, 2022 exams. Till we meet again.